Thank you for the invitation to be here, which is really a great honor for me and a great pleasure for being here talking, here listening, here meeting people. And I'll say a few more words if I'm not too late. This is the light, okay. I hope to do the same that Mireille Busquemedou did in her talk, which is to end up with a problem, which is an open question that could sneak into the agenda of Philippe in his spare times, and the problem to be cute enough and simple enough that you can do that in a corner of a sheet of paper. Let's see if I will succeed in that. I'm starting with a picture. This is in this quiz, one of those fully packed loops configuration that emerged a lot in those old Rasmus Toganov times. And we will see how it will pop up with new things today. But before doing that, I shall give some preparatory material in order to explain why I'm interested into that. And that's very basic. Some facts in algebras. So in algebra you have sum and product. If you have a linear basis, the sum is described. So you have to explain the product. And the product is described by the structure constant over there. Now say that you have a scalar product over those indices, alpha and beta. And so the dual basis of f will be some basis g such that abstractly g scalar product f is delta. So the dual basis will have its own structure constants. And if you introduce the skew combination just in this way as a shortcut, in order to have the fundamental property of skew functions, which is to bring down the index in that way, you see that you have to use the structure constant C and D in a crossed way. Just an elementary fact. And if you have one algebra that you understand well, and you define a new algebra which is a deformation of that, maybe that deformation comes with an explicit change of basis B. Most often triangular even, but you don't need that. If you call B bar B to the minus inverse, -1 transpose, so you keep the scalar product if you use a consistent way of using B and B bar on upper and lower indices in a way which is reminiscent of Einstein notations. So the new structure constant, for example, will be given by the action of B and B bar in a certain way, which is a bit messy, but it is just consistent use of indices. And in particular, Cauchy identities that you have when you have algebras of functions, they do not change because B and B bar cancel out. Period. Very simple. Sure functions. I don't know how long I should be on that. I will try to be quick, but I have to say those minimal things that will go over to something different. So, of course, the sure polynomials can be given by the Weil character formula, the famous determinant of those powers shifted divided by the van der Monde. I call delta this triangular integer partition n-1, n-2 up to 1. There will be a recurrent notation. And the idea is that when you introduce the e's and the h, you can also use the Jacobi-Trudi formulas, the normal one and the dual one. And the nice fact is that in this case you can also use infinite alphabets, and the things are well defined. One special alphabet which is infinite with respect to use of h and e in Jacobi-Trudi, but in fact gives finite polynomials, are supersymmetric sure functions. And the supersymmetric variables are exchanged by a famous omega involution that I will try to demystify a bit, but it will not be anything original, you will see, by telling that a supersymmetric S lambda of x1 xn y1 ym is S lambda prime of y prime 1, y1, ym, x1, xn. That means if you take the transpose of the integer partition and exchange bosonic and fermionic variables, in a sense, you have the same expression. A nice fact is that when you define these Q-Schur polynomials in terms of semi-standard Young tableau, those satisfy the fundamental property of skew expressions in the way of scalar product, as I told you in the beginning. In this case, when you take as scalar product the formal Hall scalar product, which is the normal one, the famous one. And you see again the appearance of, so the Littlewood-Richards coefficients exist for those polynomials because that's an algebra, but they also emerge when you want to multiply, of course, but also to split the skew functions. And all in all, the Littlewood-Richards coefficients appear in three different problems, which is multiply Schur functions, decompose a skew Schur functions, and split an alphabet. If you deform Schur functions into other families of polynomials, what normally occurs is that you are using some change of basis, and the basis and dual basis will not be the same in general. So the same of these holds, but you have to be careful where you have C and where you have D. Just that, period. A lot of people here, and Philippe in particular, will maybe share my opinion that my feeling on Schur functions is that they are partition functions in certain geometries of certain integrable models, very simple ones, free fermionic. In this case, they will be given by certain weighted Lozenge stylings in which you have a variable xi if you have a green losange at 8 height. And it's better to give weights only to green ones, because in this geometry you have infinitely many yellow and blue, so you better give weights 1 to them. So this is a kind of bijection which is immediate from the semi-standard Young tableau representation. So you have skew Schur functions being described as a counting of Lozenge styling. It's a matter of taste to take lozenges with 60 degrees and to straighten them up into squares. But, well, I do that here because using squares is kind of compulsory in order to describe in a compact way supersymmetric polynomials. So I will stick to this notation for a long while. So this is the set of vertex weights when you want to make this Lozenge styling representation of Schur functions, and actually those are just those lozenges cut in a smart way. Another way of doing that would be by cutting on 45 degrees, in a sense, with this other matrix U that essentially makes the same up to a shift. So far so good, and the idea is that there is a notion of bar. It's not the same bar of before of B bar. This is a bar that is intrinsic to the description in terms of path of these partition functions. The bar of something will be, in my case, always you flip, I guess, this way and exchange blue and green. So T bar will be the matrix obtained by this operation, but this operation passes over to the diagrams. So if you flip over the whole diagram and exchange red and green, you have a diagram of the same type, but this time not for things going from mu to lambda using a bunch of t and then a bunch of t bar, but from mu prime to lambda prime using t bars and then t's. And this is telling in one picture, just with a rigid symmetry, that supersymmetric skew Schur function S lambda x y is equal to S lambda prime y x. You can't forget that now that you see that, and the same happens for use semi-rule on the weights. So the normal way of telling the rules is by telling that you go up by one single layer by adding horizontal or vertical strips, according if you use t or t bar, to the integer partition. And so you have an algebraic formulation on what is S lambda mu in terms of a bracket of operators which are transfer matrices in a sense. This fact is well known, of course, and has led, for example, among other things, to the famous analysis of Schur processes. And what I want you to retain from this is that t and t bar acting on the appropriate empty integer partition make make the empty integer partition, and the t's and t bars commute. They actually have these also interesting commutation relations which are at the basis of the Cauchy and dual Cauchy identity, but I will not talk about this much today. This is a beautiful piece of math that is not due exceptionally to Philippe, but to Paul, close neighbor. I don't know if it is here. It's a beautiful paper that you really can't forget when you see that for the first time. And it's telling a long story. Little-Richardson coefficients have been described by Little and Richardson notoriously in terms of certain Young tableau with numbers on that, certain rules, a bit complicated. And Knudsen and Tau described them in terms of puzzles, which are some tilings of a triangle with boundary conditions, which are somehow the lambda, mu, and nu of your C. And those puzzles have been interpreted also as square triangle tilings of a certain domain by Potts-Justin in this paper, and they have been identified in retrospect to be the Little-Richardson coefficients, because if you look at this way in which the Little-Richardson coefficients may appear, you can identify this equation as being a consequence of Yang-Baxter on a suitable domain in which the two terms of the equations are realized by taking a certain sequence of transfer matrices and then making them commute. And these transfer matrices, they are not like Schur, which means two colors of path crossing each other, but they're a bit more complicated. There are three colors of path here, except that the Schur terms occur in certain part of the geometry in which of these three colors there are only two of them occurring. Let me show that with a picture, which is in fact actually the same picture taken from Paul's paper. In this geometry I have a bunch of t bars, a bunch of t, and then certain t zeros that actually here they have a trivial role because everything is the empty partition. So S lambda xy is just this one by definition. And it's the left-hand side here. But then you move the t's and t bars above the t zeros. And what happens is that here you have a triangle in which there is a mess. You have both red, green, and empty, which is white if you want. And goes from lambda to some mu and nu. Then the mu and nu, you see, they just travel in these triangles straight and go with a sort of identity. And they go also as an identity in these two parallelograms. I don't know how to say that, in these two strips. And then here and here, something happens on the green and on the red with the t's and the t bars, and the mu and nu prime in this case, they are brought back to the full red, then full white, and full green. So in one picture, let me show it again, you see that these tilings must be, by definition, the structure constants of the Schur functions. It's forced. And as they are identified to the Knudsen-Tau puzzles, it is a different proof that the Knudsen-Tau puzzles count Little-Richardson coefficients. And the Little-Richardson rule counts Little-Richardson coefficients. It's beautiful in a sense that once you see this picture again, you can't forget it for life. I hope you agree. Time to go back to the past, in which there was a lot of activity on Razumov-Stroganov, and in fact we have seen in Paul's talk a very long list of papers that were more or less related to Razumov-Stroganov, and which involved Philippe, including the very complicated ones on QKZ and everything. Two of them, they are smaller papers, which were more specifically conjecture papers. And I pointed them out because, as he said, talk about conjectures in a sense. And the Razumov-Stroganov thing was something that played an important role in my career. And I have to thank Philippe for his inspiration, both in his work and discussion and everything. And I must say that in this sense, it was a turning point in my even personal life, if you want, by moving from Italy to here and everything. Let me go back to the story. So let me puntualize an important fact. There is the Razumov-Stroganov conjecture, the one that appeared in the first paper, but it is more fair to say that there is a whole family of Razumov-Stroganov-like conjecture, which are very similar to each other, more or less in the same way that a given integrable bulk model may have different boundary conditions which are integrable and things like that. And it is very combinatorial in a sense, and it is really something that you get hooked to. Let me remind you that a link pattern is just a pairing of the points on a total cyclic ordering, if we want, which is non-crossing. Nothing more, nothing less. If you open the cyclic ordering into a linear ordering, the arcs can be represented in an analogous way and can be transformed into straight lines, if you want, by taking them upwards. And if you take the complementary of those segments, you get an integer partition, which is boxed into delta n. So just remember these link patterns are like integer partition boxed in delta n by a simple bijection. And then there is this picture of the cylinder we've seen already in Paul's talk, that if you fill it with 10 Philippe tiles just by coin tossing, defines for you probabilities for link patterns that will give you some probabilities, in this case, for this Markov chain, if you want, of adding one extra layer, all probabilities as the process. And then you have these fully packed loops. Now you fill up the square with these alternating boundary conditions with these 6 tiles by being careful so that the tiles match each other. And then you look at the black link pattern. Not the white by now. And not also the potential presence of loops, which are absent in this small example, but they will be present in general in large examples. And the conjecture that then become a theorem at some point is that the probability that a given FPL has a given link pattern is the same as the probability that a random infinite configuration on the temporally model has the given link pattern, which is this. So this was conjectured for the square domain here in a paper by Razumov and Stroganov 2001. I call it 2001A, the first one of two that appeared in that year, and has been proved by Cantini and myself in 2010 as the preprint year, I guess, for all families of domains that we call dihedral domains. So the idea is that there is a dihedral invariance in this problem, which is, in order to be compatible, it must be the case that enumerations of fully packed loop configuration with a given link patterns must be rotational invariant. There must be as many as with a given pi as with the rotated. This has been proven bijectively by Wieland, and if you look at the bijection, you understand that it holds in a whole family of domains, and in fact in all those domains the Razumov-Stroganov conjecture did hold. But despite the fact that the Wieland lemma works with two link patterns that you can define, and also with a number of loops, here you have a loop, we never managed to use these to make a richer version of that. And the conjecture exists also in a vertical version, thus using vertically symmetric ASM, which is in a sense the open version of the spin chain or loop model. And this conjecture is open so far, and we have been thinking about that repeatedly because it is unsatisfactory that we don't have a proof for this. We think we understand the whole family which generalized the dihedral domain in the vertical case, but we don't know why any of these domains satisfies the conjecture. And so here's the question. We do something crazy. Despite the fact that we never proved any vertical Razumov-Stroganov conjecture, and we never had an idea on how to construct any dihedral Razumov-Stroganov conjecture using the triple enumeration, now we look at fully packed loops which are pertinent to the vertical and with the triple enumeration. Why? Just because. In this simple example, you see that I'm also counting them according to the number of black arcs on top. And you see, here there is 1, 1, 1. 2, 2, 2, 1, 1, 1. This is strange. If you do that on larger examples, you soon realize that there is a factor 1 plus y to the n popping up if you give a weight y to the black arcs if you want, even if you take separately pi black, pi white, and the number of loops. Which is crazy because even just the fact for tau equal 1, which is not counting loops, summing over pi y, even that, it's a conjecture by Cantini and myself, unpublished as many others, but it's still conjectural, and it's weird. But now we have the stronger one. It's not stronger of something published, but whatever. This 1 plus y to the n pops out of the enumeration. First conjecture. Many one are behind the corner. Now we play a different game. This is the enumeration before. We only keep the white ones without loss of generality now that we have the first conjecture. And you can make the table and recall the fact that here there is a loop, so you put a tau. So this is the table in larger size. And I told you that there is this simple projection with integer partitions, so let me draw the integer partitions instead of the link patterns and record the number of cells in the integer partitions. So this is the table, this is the larger table, and you look at it and you start seeing that something weird is happening. And you have these many conjectures. Second conjecture after the first one of the 1 plus y to the n. The degree of these polynomials in tau are very simple. They are just the sum of the degrees here minus the degree of delta n. In particular, you have zeros if those degrees are predicted to be negative. Then the enumeration have defined parity. Not clear. The number of loops. The loops could be anywhere. And then this conjecture 4 is puzzling. We have 3 involutions. Lambda rho equal rho lambda. Okay, come on. That happens. Lambda rho equal rho prime lambda prime. And then the third one. Lambda rho equal lambda rho prime. So 1 is easily proven if you know VLAND. You do VLAND in one of the 2 moves that you have, and then you swap black and white. And 1 is done. So 2 would follow easily, even more easily, by doing a vertical reflection and swapping black and white, assuming that conjecture 1 holds. And 3 is mysterious. And then you have conjecture 5. Those polynomials which have degree zeros, they are Littlewood-Richardson coefficients C lambda rho delta n. Littlewood-Richardson, I mean, even in this big table, these 2, which is the first one, which is not 1. And I mean, I didn't show you the bigger table because they don't fit here, but Mathematica did. Another puzzle, are conjecture 4 and 5 even compatible? They are compatible, but for a strange reason. Did you ever see lambdas which are declared to be such that the Littlewood-Richardson coefficient C lambda mu nu is equal to C lambda mu nu prime for every mu and nu? There will be a magic property for lambda. Let me call magic a lambda such that does that. And triangular, a lambda which is a triangle. Fact, triangular equal magic. You are magic even only if you are a triangle. And the fact is nice. It is somehow a fact, and maybe unobserved fact, on these Schur processes, that T and T bar have the same action on delta n. Because on delta n, removing an horizontal strip and removing a vertical strip is the same thing, is removing some corners. So when you have this, you can swap the alphabet for free in a skew-Schur function, and then play a little bit and deduce that delta n is magic. And for the corners, it's easy. So we have a mystery. We have a full table of which one thin layer is Littlewood-Richardson. What if there is a deformation of Schur functions into something else? Hall polynomials, Jack polynomials, Grothendieck polynomials, whatever, such that the structural functions of the deformation are the full table that I see in fully packed loops. That's what I will try to say in my 2 minutes, that it kind of works, but only for the top term of the polynomial. If you do this deformation of putting minus tau here, and this is done unambiguously. There is no more freedom in doing that. And if you do that, you are adding a minus tau in the cells which are preceded by one of the same number, which is here, those which go straight. If you do this, you happen to realize that the new functions are obtained from Schur by this change of basis, which is also described by Lorenz-Stiling, whose inverse is also given, And there are very explicit functions of which you have analogs of Jacobi-Trudi formulas and things and valid type formulas. And those functions, they are not unknown. They are somehow already appearing around under the name of canonical Grothendieck polynomials, despite they do not appear exactly by my weights, because they come from bosonic vertex models. And you can do also the dual function by a similar procedure, and which have similar formulas. And so the increase of conjecture 5 is this bigger conjecture, which is telling you that the top degree coefficient in the whole table is the Littlewood-Richardson coefficients for those canonical Grothendieck. And this is good, because the T's are deformed, but they have the same nature. And the proof telling that triangle is equal magic works out of the box. So this was needed for the construction to be consistent with the conjecture observed. But the problem is that I'm not able to construct the full polynomials appearing in those tables by doing a second layer of deformation. The candidate model, which will be a full-fledged 6-vertex model, makes things which have the good structure in terms of powers of tau and everything, but they do not give the true polynomials, and I may be stuck here. And well, this is the rule for the 6-vertex model, which is puzzling because it was not even guaranteed to be an algebra, but it looks to be empirically an algebra. And this is the final slide in which I do a summary of the open questions, but I hope that some of the open questions that I spelled catch the attention of Philippe. That will be an honor and a pleasure. Let me thank you again and wish you.
Thank you very much. So, any questions?
Right. Yeah, it's a comment in the question. So first, a comment that, as far as I understand, once you reintroduce tau, which is the weight of both white and black loops, right? Is that correct? That I understand correctly? Tau is the weight of the loops?
Tau is misleading here. Tau is the weight of the loops.
Yeah.
But in this Grothendieck stuff, tau is just a grading, so I can eliminate it. It is for granted. The polynomials are homogeneous in a sense, so by homogeneity you can reintroduce it. And tau will be in the good place only if this worked. So my hope is that this worked with omega equal 1 or minus 1.
Right.
If it did, tau cannot be eliminated. But in the 5-vertex model, tau has a fake role.
Right, so let me get to my comment. Is that, so as far as I remember, this is an integrable model as well, when you put a weight of tau for white and black loops, but it's a rank 3 model, sorry, rank 3 model, not rank 2 model. Is that, I think I remember, if I remember correctly, this is all work of...
I understand what you're telling now.
Jesper and myself.
An old paper of you and
Jesper, if I'm not mistaken, yeah.
Which has the trouble that is very difficult to read.
So, well, okay. I'm not sure how to answer that. But anyway, my point was simply that then it kind of suggests that you're not really multiplying rank 1 wave functions, but rather something which is higher rank, because you're already moving all the way to rank 3. So that's just a general comment. And also, now my question is, there was also work of Nadeau and collaborators where they also had Littlewood-Richardson coefficients appearing as limit of fully packed loop models. Is that somehow related to your work?
It is the things which is more near, but nonetheless it's very far, for a deep reason. In these tables, so they have the same as here. They understand that the Littlewood-Richardson are a sector, which is a thin layer of something that is on one side filled with zeros, and on the other side filled with unknown stuff. And in this case, the side in which there are the zeros and in which the things is unknown is the converse with respect to Nadeau. But which is not too bad, because the C's and the D's tend to have opposite behavior in this respect.
I see.
Okay. Do we have other questions? Okay, so I think we should thank again Andrea. Thank you.